Finished your PhD, I'm guessing, in 2014 at the University of New South Wales under Professor Rob Brander, really looking at rip currents and spending a lot of time driving on a jet ski. Since then, he did 1 year as a teaching assistant and researcher at the University of Sydney. And then since 2015, 2016, has been based in Plymouth in the UK at the University of Plymouth, and has subsequently just in the last few months returned back to Australia, and it's great to see him back as a familiar face. So Jak is going to be presenting today on a lot of the research he's been doing at the University of Plymouth, and specifically on can transport from the lower shore face save beaches from sea level rise. So something that I'm particularly interested in. So I look forward to seeing you talk, Jak.
Cheers. Okay, I'm just sharing the screen now. Thanks, Mitch. Thanks, everyone. And I'm aware I'm definitely not one of the bigger names that's presented at this thing recently, but thanks for coming along anyway. And I think this is going to be quite an interesting talk. I've done a few presentations recently, and I know some of you have attended those, so I wanted to produce a bit of new material. And what inspired this fairly provocative title was some conversations with Het Maslink, who's woken up very early to be here, and also some brief discussions with Mitch. For example, last time I presented, Mitch was asking a question about this stuff. And so I wanted to investigate it further. So I'm going to present on some of the work that has been done at this beach here, Perranporth, in the UK. And then I'm going to expand out on that to explore whether it is indeed possible transport from the lower shore face could save some beaches from sea level rise. Okay, I'll go through some things on sediment budgets to start with on wave dominated beaches, and use this to lead into with this idea of transport to the lower shore face. What is it? What do we know about it? Then present on some existing results from Perranporth, and then expand out into some more exploratory stuff on Perranporth. And then right at the end, I'll just look at the flying to Narrabeen briefly, and hopefully provoke a bit of conversation about that. So this is where I've been here at Plymouth for the last 4 years. This is the southwest of the UK. The two main beaches here we've been looking at, the north coast of Cornwall is Perranporth, and the other one here is on south coast of Devon in Start Bay. But we're going to be focusing in here on this the wave exposed side of Perranporth. So this project had a huge amount of fieldwork, monthly, quarterly, annual surveys, storm surveys, and boat surveys, and quad bikes and drones, as well as a bunch of modelling involved. Here's a quick shot of the team. There's Het up there. I especially want to thank Nieves Valiente, who's now at the Met Office, for a lot of the great work she did over a PhD at Perranporth, a lot of which I'll be talking about today. So I wanted to spend a bit of time on background here, looking at a sediment budget equation. So this one comes from Dean and Houston 2016, and I've simplified it as much as possible. So we can express shoreline change as a function of sea level rise translation, and then the other components, across shore, along shore, and other inputs and outputs. And I'll go through each of these briefly in a graphical way. So for sea level rise translation, we start by defining something called the active profile. And this here, there is quite an assumption involved here that we need to rely on, in that this part of the profile will maintain its shape over longer time periods, say over several years or a decade or more. It'll shift onshore, offshore, up or down to conserve total volume. So if we got the width of the active profile, the height of that active profile, we've got tan beta as the gradient. If we then apply a sea level rise, then we've got this traditional concept of the Bruin rule, the simplest way to apply this sea level rise translation. And we simply make an assumption that for a given level of sea level rise, the amount of onshore transport will simply be the sea level rise divided by the profile gradient. All right, there's this profile shifted onshore, the initial shoreline and the final shoreline. So that's the classic Bruin rule. Next component of a sediment budget is net cross-shore flux. So this might include onshore transport from the lower shore face, that we'll get into more detail on that in a second, dune encroachment, dune accretion, and this volume here will be a function of the height of that active profile by the change in the shoreline position, or we can express this as the change in shoreline position being the change in volume divided by the height of the active profile. Similarly, for other inputs and outputs, imagine this coming in or out of the page or just being dumped in terms of, say, a nourishment, other volumes that are added to the profile. Similarly, we can express this as the change in the shoreline position as the volume over the height of the active profile. So this gives us a nice set of rules that govern how we should think about the sediment budget. And then an additional interesting question to ask is how much extra sediment is required to offset potential sea level rise. So that's in order to get no shoreline change, delta x equals 0. If we rearrange here, we can get something I call delta V offset, which is simply the change in sea level rise times the width of the active profile, which is a handy little number to use. For example, what's the offset volume for a metre of sea level rise over 100 years with an active shore face 1 kilometre wide, so 1 times 1,000. If we express it as a rate, that'll be 10 metres cubed per metre per year. And anyone that's not familiar with this, these units, this is metres cubed in volume added to the profile per metre along shore per unit of time, which here is a year. So another example, this is important. If the same profile is presently stable and current sea level rise is 2 millimetres per year, what is the current budget? Well, just to keep things stable under our set of assumptions, we need 2 metres cubed per metre per year. So that's important to remember as well. This is a conceptual model for Embayed beach sediment fluxes I've been putting together. I'll find a use for this soon. We're here thinking about an embayed beach with a couple of headlands, waves coming from this direction. We've got sediment fluxes split into cross-shore or long-shore and inputs and outputs. And then we've got this active zone that we've already talked about. And then beyond the active zone, we've got the lower shore face and then going into the dunes or the back barrier in the estuary. So the components of the budget that we're interested in are, firstly, there's storm response and recovery, but this is short-term variability that we're not so much interested in. We're more interested in trend changes beyond the active zone, either with the dunes or, as we're going to talk about more, with the lower shore face. The other components of the sediment budget that are really important for the discussion we'll go into are headland bypassing that can add or remove sediment from the embayment, and also mega rips, which might remove sediment from the active shore face potentially quite quickly and move it back to the lower shore face. Just a caveat here that large fluxes to deltas in some areas where you've got large flood tide deltas, such as where I am now at Port Stephens, and think of Jimmy's Beach here, these can overwhelm a lot of these calculations and make them quite meaningless. But I'm not going to talk about those situations with large flood tide deltas now. Okay, on to some background on this idea of transport from the lower shore face, in particular onshore transport from the lower shore face. We'll now define the lower shore face as this area below the active zone, and it can be quite hard to define what that active zone where it ends, but for now, let's just say that potentially goes all the way down to wave base, the lowest point where waves interact with the bottom. We've got the forcing is through wave shoaling, asymmetry and gravity, potentially gravity transport, and transport rates will decrease with depth, as indicated here from the Cow and Kinsella model. Another Daly and Cow conceptual model here shows that we've got 3 potential scenarios: a shore face that's in equilibrium with the last phase of sea level rise, and then 2 potential situations, one's called underfit, one's called overfit, where the shore face has not caught up with the last phase of sea level rise, and we've either got positive or negative accommodation space, which over time in an underfit scenario will have offshore transport, and in an overfit scenario will potentially get onshore transport. So this is very much a sort of conceptual understanding. It's very difficult to get field data on these very small amounts of transport occurring on the lower shore face, and there aren't a lot of people looking at it. Mike Kinsella and Peter Cowell are some of those who have. but it's certainly interesting to think about what could be going on down there. And the idea or the hypothesis is that there could be many of these overfit shore faces where the trend is for onshore flux, and that may be quite common in New South Wales and other coastlines globally. So we'll look at a few of those examples. Firstly, for the same paper that we got the sediment budget equation from, that gave us a framework of how to think about these things, rates of onshore transport, Florida from the US, from Dean and Houston there. Now here, it can be difficult to directly measure these rates of onshore transport. So what was done here was to determine all the other components of the sediment budget, and then whatever the residual was determined to be the rate of onshore transport, which is about 3 meters cubed per meter per year in this scenario, or for this setting here in Florida. And here is, on the x-axis is showing the width of the active zone against what I was calling the offset volume, but here you can think of the amount of beach nourishment you need to do to keep the shoreline where it is. And for the high emission scenario, 8CP, RCP 8.5, was determined about 5 to 8 cubic meters per meter per year would be required for offset. And that was discussed as being a relatively modest increase, the current nourishment programs in this setting, where in Florida, a lot of nourishment's already going on. And then for New South Wales, some examples here, as I mentioned, Mike Kinsella and Peter Cowell especially have done a lot of work in this area. So this is from a few years ago, looking at the Foster-Tuncurry barrier with a potential rate here for shoreface driven sand of 1 or 2 cubic meters per meter per year. Other figures from some of Peter Cowell's older stuff for similar ranges, 3, 2.5, and other coasts, maybe 5 in the Netherlands. And the northwest of the US, potentially a much higher rate there. But most of the figures are in that range of about 1 to 5 meters cubed per meter per year. And when I've applied this to some of my work in the past, I've gone for that fairly conservative range. But as I'll go on to show, potentially it's plausible that higher rates might be occurring on some coastlines. Okay, that's enough for the background. We'll now go into the site and the results section on Perranporth. So this beach that I have spent a lot of time walking around on for the last 4 years, it's macro tidal, 6 meter spring tidal range. It's about 3.5 k's long, the embayment. Big headlands at either end. Gets powerful long period waves, especially in the winter. It's cross-shore dominated, but as we've gone on to find out, the sediment budget is quite open, and there's a lot of interesting stuff going on the lower shore face. So here's the first of several figures I'll show from Nieves Valiente's work. So this is a digital elevation change model constructed from multiple sets of surveys combined together. And what you can see here, just in this example, I think this is from 2016 to 2018, but there is a lot of change occurring outside this yellow line, which is the supposed depth of closure. So potentially, even at these very large depths, there's detectable change going on. And what you can see on the right here is wave height in a series of volume time series. Because this is all quite complex, I will cartoonify it and simplify everything. So now think of the system as being comprised of dunes, intertidal, subtidal, and this area of the lower shore face. If we look at waves, wave power in this environment over time, you can see winter wave peaks, and then the big one in 2013-14, biggest winter storms in 75 years or so at least. If we look at the impact here on the dunes, mostly stable or even prograding slightly. It's hard to tell over this range, but certainly there's one big drop after that big winter. Then in the intertidal volumes, what you can see is a very definite annual cycle of about plus or minus 50 cubic meters per meter per year. And then potentially we can see what we'll call an extreme event cycle over a longer time period with about 5 to 7 years for full recovery. It starts to get interesting when we move down into the subtidal, because what you can see happening here is the range of variability is about the same in the intertidal, but the two we initially expected to see a strong inverse correlation. And in fact, you don't see that. The two are poorly correlated. And the reason for this is that there is a lot of action going on in and out of the total system. This could be due to headland bypassing, and transport, cross-shore transport with the lower shore face. You can see there's a very large range of variability there over relatively short time periods, and there's certainly no discernible trend. So looking in more detail at constructing, still from Nevis's work, some of these sediment budgets over two different epochs here. So from 2011 to 2016, 2016 to 2018, there's these wildly varying changes in the total sediment budget for the full embayment. So over the first time period, the system's losing about 100 cubic meters per meter. And then in the second time period, it's gaining more than double that. And if you take this as a rate per meter along shore, I'll just give a rounded figure and say that it seems to be potentially over 10 meters cubed per meter per year. So that's an important number to remember for when we go on to exploring further in the next slides. Here, there's a model that's been constructed also by Nevis showing that the system potentially gains looking at potential sediment input. So here, assuming total sediment coverage and infinite sediment depth. This is a factor of 2 or 3 larger for that due to those assumptions than the field observations over the same time period. But the two are entirely consistent, that there is potentially a large positive sediment budget over those types of time periods. So looking at 3 initial scenarios that were proposed, a closed sediment budget, open and balanced, and open and unbalanced, it's this one. Definitely this one it appears to be. And that was a surprise to some degree. Okay, so let's think a bit further about if we've got this wildly varying total sediment budget, what are some of the processes driving flux with the lower shore face? And it's going to be quite different than those series of processes I talked about earlier about this very gradual onshore flux. If we go back here to the RIP review paper in 2016, we talked about the concept of embayment scale circulation. So this is where you've got big waves and a very large surf zone relative to the length between the headlands, so that the headlands, the geometry of the headlands shapes a circulation cell which fills the entire embayment. And as part of this, you'll see mega rips. But the mega rips are just part of these embayment scale circulation cells. And then to go one step further from that is you go from high waves to extreme waves, and also on macrotidal beaches where you can move the shoreline a long way offshore at extreme low tides. You have the potential here for breaking way outside some of the headlands, generating what we're calling multi-embayment circulation. So now you've got more distal headlands beyond the initial headlands shaping this large-scale geologically controlled circulation. And what we found here over a series of different models is you can reverse the transport at various headlands and also shift the position of mega rips and move a lot of sediment around in ways that is not clear what is cross-shore transport, what is along-shore transport. So here is something that I've just started thinking about, potentially a new conceptual way of understanding some embayed beaches. So at one end member, we've got, we'll call it a slow change model. And this is where we've seen gradual onshore flux. Maybe there is some bypassing and mega rip action accounted for, but they're generally all on the order of a cubic meter per year. And it'll be very hard to detect change in this hypothetical system over short time scales. So that's one way of thinking of an embayed beach system. Potentially what we need to think about is another model, which we'll call fast change, where we see rapid influxes in and out of the system to the lower shore face. And this includes a combination of cross-shore flux, bypassing, embayment scale and multi-embayment scale circulation that it's difficult, very difficult to differentiate between. In this instance, the budget won't balance, and any trends will be obscured in the short term by this huge amount of volatility in the total system volume. So really, these things, you know, these are end members and there's a spectrum continuation between them. But it's just an interesting dichotomy to think between these two types of systems. All right, before we go on, I'll do a bit of the exploratory testing of the whether the potential inputs from the lower shore face are going to be enough to offset sea level rise. I'll talk about a method for doing this. This is the shoreface translation and sediment budget tool that I've been working on. This is a really convenient way for taking that sediment budget that we went through earlier in detail and then applying this across a 2D profile. So here it is showing us an example for Perranporth and for the other beach that we've looked at in detail, but I'm not talking about here today, Start Bay. This combines aspects of Peter Cowell's model, the Atkinson profile translation model, this idea of wall demand from abuse and paper, various other aspects, and it also includes trend sediment flux with the lower shore face. There is a preprint of this still available. It was going to be in coastal engineering. It doesn't look like it's going to be there anymore, but that'll be out somewhere soon. So that was the tool that's used to investigate in 2D some of these sediment budget rules. So we're now going to saying for Perranporth, are observations consistent with lower shore face transport? And we've pretty much shown that already. But if so, is it plausible that there could be enough to offset sea level rise? And we're using our example 1 metre over 100 years. Remembering that the width of the active shore face is important. And at the northern end of the beach here, it's about 800 metres. So I'll use that number. And that works out to our offset volume being about 8 cubic metres per metre per year. That would, if we're getting that much input, it's enough to offset this much sea level rise over that time period. So here using that shore trans tool, applying 1 metre of sea level rise over 100 years with 8 cubic metres of input split between bypassing and onshore transport, because it's very hard to differentiate between those. This is what the profile looks like after 100 years, that you've got deflation of the lower shore face, aggradation of the active shore face, and zooming in at the top of the profile here, it's essentially just moving the profile up by 1 metre so that you've got very little change in the shoreline. So that's just a way to visualise it. That tool is handy for doing that. Now what we're going to do is show the contour position of mean sea level. And we're also looking at what's a little bit more stable is the mean high water level. So time series of both of those going back to over the survey period back to 2007. And what we're going to overlay on the top of that is using these sediment budgeting principles is the coloured lines here are the projected mean shoreline for various input levels. And what we're doing in this exploratory phase just now is just testing which of the coloured lines could potentially fit the actual trend in the observed data. And as you can see here, there's so much short-term variability that really any of those trend lines could potentially fit. So it's not particularly useful. However, what if we look at the dune vegetation line position? Now, I've obtained this time series using Killian Voss's COSAT and using the NDVI index to look at the vegetation line. This certainly could be improved. It needs to be further validated, but for our purposes here today, it's interesting just to have a look at it. If we fit a trend line through this, then what this is saying is the dune vegetation line with this smooth line here may have prograded 10 metres or a bit more over this 35 years or so. And if we now overlay the dune line projection, and remembering we're not looking at necessarily the same thing here, the vegetation line and the dune toe, but in any case, if we assume one's a proxy for another, which of the coloured lines potentially fit the actual trend in the data? And without overstating this too much, because it certainly needs further work, the higher input levels are consistent, most consistent with the trend in the data. So what this is saying is that at this stage, I would say it's certainly plausible that the data, that the observation are consistent with there being enough input to the Perranporth system that even relatively large amounts of sea level rise could be offset. And I didn't expect this. When I set up to do this talk, I thought I'd set it up and knock it down to some degree. And so I found this quite interesting. Interested to hear what Mitch and Het have to say on this, what their findings have been. They're looking at similar stuff. But yeah, let's just go through the lines of evidence quickly. The observation and modelling that we talked about earlier suggested sufficient input may be occurring. Remember, we used that number of 10 cubic metres per metre per year, but there was a huge amount of variability. We don't know what that's going to look like over the long term. In the short term, looking at the shoreline position, there's just too much variability for it to really be useful. So what we've done instead is looked at projections of the dune line against the dune observations of the dune vegetation line obtained from satellites, acknowledged that that could be improved and developed further, but we'll at least say at this stage, it seems quite interesting and the hypothesis seems plausible. So for the last couple of minutes now, before I finish up, I've had a quick look at applying these thoughts to the narrowbeam data as well, and I've only spent 3 minutes looking at narrowbeam, so I'll defer to others on what might really be going on. But anyway, my thoughts will be presented now. If we've looking at the profile in the middle of the beach, so we reduce the impact of rotation. Thank you to WRL for all the data. Grey is the envelope of the topo profiles going back to mid-1970s. And the coloured lines here this time are projections of slightly lower input rates and how the profile would change if we had 44 years of 2 millimetres of sea level rise per year with these levels of inputs. And in this instance, because we've got a much shorter width of the active shore face, we're going to be looking at numbers. Our offset volume is going to be more like 3 or 4 cubic metres per year, with potential for some uncertainty around that, but they're smaller numbers than at Perranporth. So that is just a visualisation. You can see that if we look for that yellow and orange line in here, they're very much buried again within the envelope of short-term variability. And if we go into the time domain, again, what we're looking at here is shoreline position in the grey, 1 standard deviation for the dashed lines, overlaying projected mean shoreline trends for given levels of input. And I haven't accounted for potential other factors in the sediment budget, and asking ourselves the question, which of the coloured lines might plausibly represent the actual trend in the observed data? And again, here, there's so much variability that it could really be any of these, except maybe potentially the red one there, but even so, without having done any statistical analysis on it, I'm sure they're all they may fit within the 95% confident intervals. But now let's look at the position of the dune toe, because this is more stable over time. And we can use it as another proxy for the total system volume, which is essentially what we're doing with the shoreline. But if we use the dune toe, it's more stable. And you can see here, again, we've overlaid the projected future shorelines for given rates of input. And it's a little bit more questionable here as to whether some higher rates of input are consistent with the data, or whether it's more likely, one of these lower levels of input. But I won't go into that any further. I won't come to a decision because, like I said, I've only looked at this data for a couple of minutes, and it's really something to get Mitch's thoughts on. And reiterating again, I haven't accounted for other aspects of the sediment budget. Okay, I'll wrap up before we move on to a discussion, but I think it's really useful to apply these basic sediment budget principles to test hypotheses on how shorelines might change in future. There's the sediment budget approach, is that equation that we looked at earlier, and then there's that ShoreTrans tool that I've been using, which is a really useful approach to modifying the two-dimensional profile. And then after introducing the concept of transport from the lower shore face, we then looked at the example of Perranporth and showed that you know, there's potentially an end-member slow change model where we've got this very gradual transport from the lower shore face, which is hard to pick up on, as opposed to a fast change model where you've got rapid inputs, potentially from quite substantial depth and from around the headlands that are being pumped in and out of the system on relatively short timescales over the course of a few years, and that this may be more common on, particularly on high energy macrotidal beaches with fairly wide, flat, active shore faces and lower shore faces. And having looked at some analysis, exploratory analysis of the fluxes that may be coming in and out of the system, we reached the rather interesting conclusion that it seems at least plausible that the fluxes into Perranporth may offset moderate to even higher levels of sea level rise that will induce shore face translation. However, at the other end of that scale, it will be much worse for other areas that are potentially losing sediment due to this mechanism of a fast change model. Or if we went back and measured Perranporth over the course of 50 years, we might find that, you know, over the longer term, that system is in fact losing volume as well. It's just not possible to tell with the length of time series we have at the moment. Okay, that's all I wanted to say. And I might unusually ask the first question and say to Mitch, what have you guys found on this stuff? Is it consistent with this, or is it something completely different? And Het, because he's in here as well. So thank you.
Thanks, Jack. You're not allowed to ask us a question.
Aha.
It's the other way around. Yeah. So first of all, yeah, thanks a lot for the talk. If anyone has any questions, you can please raise your hand now or put them in the chat, and we can go about asking them. So you asked me my thoughts on it. Yeah, I think it's an extremely interesting issue. So just for background, we're looking at a similar kind of thing, and we've been exploring looking at the total profile at 3 different sites, one at Narrabeen, at Perranporth, and also in Mexico. And what we find when we integrate the sediment budget over the entire profile, that in these looking at extreme events, so measuring the beach immediately before and immediately after extreme events, we actually find a net positive increase into the system at some of these extreme events in the order of between 50 to 150 cubic meters per meter of these extreme events. So yes, there definitely is the potential for these extreme events to offset quite a significant degree of sea level rise. So is there any questions?
There's one from Giovanni there. I can see it's a good question.
One for Giovanni. Okay.
Yeah, I should just throw this to Mike Kinsella because he'd have a much better answer than me. But I'll have a go at covering some of the ideas that Peter Kell and Mike Kinsella expressed on this. Okay, so there was the active shore face. The potential upper bound will be the depth of closure determined as the short-term depth of detectable change. And then the lower bound, you know, can potentially extend anywhere down into the lower shore face, you know, theoretically down to the wave base. So where do you pick a point to define where the active shore face begins? I think the work that Mike and Peter Kell were doing in that paper I cited there from 2018 is that the depth of the active shore face will reduce as you increase the rate of sea level rise, such that at very short, at rapid rates of sea level rise, so say at a centimetre per year, which we're expected to go into, maybe in morphological change, whereas at much lower rates of sea level rise or stalled relative sea level rise, you might be looking at double that depth or even further. Mike, did you want to comment on whatever I've missed there?
Yeah, actually, thanks, Jack, for the talk. I had you drop out there for maybe 30 seconds. I don't know if that was just me, but I caught the start of it. I actually had the exact same question as Giovanni, so I was pleased to see that.
I mean, I just take my insight into this from what you guys have done. So I thought.
Yeah, I think the caveat there, so my question was around the depths that you seem to have chosen to define your active shore face, the depths that would be consistent with an annual timescale. So say a Halamaya inner closure depth, which is basically a sediment budget for annual timescales. The upshot of our 2018 work that you were referencing is that with a fast rate of sea level change, the immediate, the part of the profile that responds in the immediate sense would shrink. But the caveat on that is the laggard response, as in the response that you're still exposed to. So the unfinished business of the system, if sea level was to stop rising, that sediment demand or potential demand is still there. So it's a sort of question of calculating the sediment volume at a point in time, or the ultimate outcome for the system, I think, in terms of sediment exchange between onshore and offshore.
And could I just say that I did expand a bit below that observable depth, and Halamaya 1 depth, but it will essentially, say for narrowbeam, for example, with the fairly steep shore face, at the lower end of an estimate of the
you cut out there, Jack.
Hello.
Must be that Port Stephens NBN.
There's a storm out there, and we lost power. And sorry, I'm back. Right, I'll try and answer that. Yeah, okay. Sorry, everyone. It is intermittent here. For narrowbeam with that steep shore face, at the lower end of estimate of the active depth, you're looking at about a 300 meter width, and at the high end, you're looking about a 500 meter width, or potentially 600. I'll get Mike to comment on that in a second. So you're looking at potentially doubling that estimate of the offset volume. And as Mike said, even if you're looking at the lower depth, you could be looking at a longer term response as you're catching up over time and continuing to lose sediment to the upper shore face.
Okay, so Hayes Young has a question related to, firstly, how to define the width. That was sort of touched on.
Yeah.
Also the driving force behind onshore sediment transport. And I guess I have a similar question related to that slow change sediment transport. How is sediment transport from the lower shore face? What's the actual process causing this slow change?
Wave shoaling, wave asymmetry, as I understand it. You've also got gravity acting in the opposite direction. So the equilibrium of the shore face is going to be a function of those opposing functions, opposing forcing controls. And then for any given sea level, for a given sediment size and wave climate, you're going to have some idealized equilibrium level. And the thought is most shore faces are either going to be sitting above that and below it. And if this hypothesis is correct, that on many shore faces, you've got an overfit profile with negative accommodation space, then that wave shoaling should very gradually, and even more gradually with depth, bring it onshore at these low rates.
Okay. Patrick Hesper, I think, has a couple of questions. Maybe, Patrick, can you please turn on your microphone if you want to ask them?
Hey, y'all. Thanks, Jack.
Yes.
Great talk.
Cheers.
What satellites were you using to determine the edge or toe of vegetation?
So again, that was COSAT Thanks.
What's the resolution?
Modifications. Yeah, so it's the Landsats and Sentinel-2. And so that's 30 meters for the low res ones and 10 meters for the recent ones. And I won't claim any of the level of accuracies that COSAT normally gets with the neural network and the pan sharpening and all of that, because all I've done is use just extracting the NDVI. So as I said, don't read too much into that. That's just sort of indicative at this stage with a large amount of uncertainty around that. It needs to be validated, and the technique could be improved by somebody that specialises in that stuff.
Yeah, okay. Just because, I mean, we've got good long-term data from, you know, a site very near where you are in Fens and Bayman that shows that the toe of vegetation, if you're surveying it with RTK or something, you know, non-satellite, that it's got like 30 centimeters change resolution. So it's a bloody good indicator of high spring tide level, or, you know, some sea level indicator. It's very good. But of course, if you're not using something with a satellite that's better than 3 meters resolution, then
it'd be miles away from that.
So my other question was, the Narrabeen always bothered me because it was so bloody wide compared to most intermediate beaches, until I realized that beach cleaning made it a lot wider than it should be. And so incipient 14 vegetation stuff never gets down to where it should be because they clean it away all the time. So is the dune toe a very accurate measurement of, you know, where that position is relative to edge of vegetation on a natural beach?
Yeah.
Beach cleaning, etc.
It's the vegetation line. Let me go back a step. What we really want is that entire 2D profile, or in 3D. That's the ideal state of information that we want. In the absence of knowing the entire profile, what we take is the shoreline position as a proxy for the volume of the entire profile. The argument I made a little bit throughout was it might be more sensible to use a higher contour, because if we're using the shoreline as a proxy for the volume, why not use another contour within the active shore face, one that doesn't vary as much? But I think once you get up into the dune, especially, you know, you go up to the dune toe, above the dune toe, looking at the vegetation line, you're looking at a different set of processes there. You're potentially getting to the edge or out of the active profile, and it may not be as useful an indicator as the trend in the system. For instance, if there are if there's dune accretion going on due to aeolian processes or other factors going on that aren't related to the active part of the shore face, or in addition to that, and then it may give a misleading indicator. But I certainly think using, for instance, the high tide line, or somewhere up near the top of the active profile, but a bit below the dune toe, might be a good proxy for the volume of the entire system.
Okay, thanks.
Any other comments on that? Because this is only something I've been thinking about recently. Did you? I saw you nod at one point during that. Do you think that's a valid?
Well, I actually thought something else really. When you talk about your slow system, where you have a steady supply of onshore sediment, it doesn't necessarily have. And then you contrast this with a much more of a high flux, highly variable system with lots of headland bypassing and lots of exchanges. I can imagine a system which is like the slow onshore one, but not a steady onshore transport, but very episodic. So I can imagine a system with a lot of production of sediment on the lower shore face, like just, for example, carbonate.
Carbonate, yeah, okay.
Perranporth, that's 50% of.
Yeah.
And then that material just sits there, and then there's a major
grows over time,
wave event,
and then it's fed onshore.
That cuts the dunes and cuts the top of the beach, but at the same time it hoovers up all that sediment that's been accumulating over maybe a decade or 20 years and
into the active system,
and shoves it into the active system, maybe 20-30 cubic meters per meter, because it's been accumulated for such a long time, it just moves that whole load into sort of the close to the depth of closure. And then in the subsequent years, the slightly less energetic conditions start moving all that stuff higher.
Yeah. And again, that's we create.
You don't need the headland bypassing large amounts to cause a lot of variability.
No,
it could simply come.
But the data suggests it is quite large from the modelling for the headland bypassing, for example. But I mean, I'd say as well that idea of carbonate production as well, I mean, that's not new. That's something that Mike's thought about in the past, and all the crew from Sydney years ago have thought about incorporating carbonate production as a significant factor in the sediment budget. I guess still with all these processes and creating this dichotomy in our thinking between a slow system and a fast system, over some period of time, over multiple decades, that is the same time scale that sea level rise operates, we should see a trend within the system. There's enough time for the big storms to have hit to bring the carbonate in. There's enough time to have multiple big storms and other systems to have reworked sediment and headland bypassing, such that over a sufficiently long timescale, we should start to see a trend within these systems. Or alternatively, the system is totally stochastic, and small changes in wave direction can take sediment out or put sediment in, and it's inherently unpredictable. I don't know what your thoughts on that are. I think, Mitch, is that something that you've thought, that these systems are potentially inherently unpredictable, or something along those lines?
I haven't quite got to that stage yet, but I think where the key limitation is that we just don't simply have enough data on bathymetric variability to even really understand it.
Yeah. So certainly, I mean, as I was sort of open-minded on this, I talked to you guys about it and thought, we'll just look at it and see where it goes. But my inclination was that the trends would be apparent even once we had 3-4 decades of data, for instance, with Narrabeen. And especially based on what you're suggesting now, that with individual storm events able to bring in 100 cubic meters per meter into the system from possibly unknown origin, it makes those volumes perfectly capable, plausible of offsetting all of projected sea level rise, which I wasn't expecting until I actually tried to pull out the budget. Yeah.
There's a good question from Colin Woodruff, which I'd like to get to. Says, I think your modelling is based on an unchanging shape in the active profile, your shore trans.
Yeah,
which seems to go way seaward of the Broome closure. How realistic do you think this is? I'm thinking of perforated barriers where a kilometre may have accreted in 7,000 years. Isn't that an enormous shape to be able to maintain that same shape? Enormous volume, sorry, to be able to maintain that shape.
Yeah, it's a big assumption. I've seen some of the... Look, it has to apply over some limited depth if you think about it, or it's a relatively good assumption over a shallow depth, because we can see and we can just understand the physics that over, let's say, Narrabeen just down to 6, 7, 8 meters depth or something. The processes operating to take sediment offshore during storms and bring it back with wave shoaling, averaged out over time. There's going to be sufficient energy in there, assuming a fairly steady wave climate over whatever period of time, that over some height of the active profile that is going to hold. The question is it really quite shallow when you can get to a depth where long-term changes to the shape of the active profile are possible, or is that, we've just gone past 2 p.m, or is that occurring at a much greater depth? And again, I would just defer to Mike on this, because he's done so much more work, and just say that a conclusion of that book chapter from 2018 was that over larger rates of sea level rise, you're looking at a shallower depth of closure, and lower rates of sea level rise, a deeper depth of closure or deeper depth of the active profile, with the caveat that even when you're taking a shallow depth of the active profile, you might be looking at a hysteresis effect and the profile catching up over a longer period of time after a given phase of sea level rise has stopped.
Thanks, Jack.
Cheers.
I'm aware of the time. It's 2 p.m. So if people have to go, thanks very much for attending. But I think this is a good discussion. So and there's quite a lot of interesting thoughts being had. So if people want to continue discussion, I'm happy for it to continue as well. Gert's still waking up, so that's okay. Mike? I'll go to Taro Arikawa from Chuo University in Japan. He's asked, from the risk management point of view, I would like to know the shoreline change rate difference between slow change and fast change. And does your results indicate that this gap will be changed due to climate change in the future?
Thank you, but maybe next time is okay. So I would like to discuss about the future. So next time is okay. Maybe the time is up.
Should I go just quickly? I was thinking the thing that defines them, a slow change system can still have very rapid, substantial changes in the shoreline. Whereas I guess what defines the fast change system is very rapid changes in the total system volume of the entire embayment. As Mitch just said at the end there, potentially an order of magnitude greater than the numbers I was talking about. And then the second part of the question was, could I get that again? The second part of the question about how it related to sea level rise, Mitch?
Yes.
Does your results indicate that this gap will be changed due to climate change in the future?
Maybe not only the sea level rise, but also the wave height is increasing due to the.
I see what you mean there. Yeah, certainly if the system's undergoes a change in the wave climate, that would, especially a change in wave direction.
Okay.
That might change rates of bypassing. And so now Het would probably be thinking about the other beach we look at, Start Bay, where wave direction is particularly important, and long-term changes, slight changes in wave direction driven by changes in the climate. And this can be responsible for rapidly rotating an embayment, changing the position of rotation for an embayment, and starting, shifting trends, clockwise or anti-clockwise rotation that can result in significant changes to the shoreline and damage to housing and infrastructure and so on, based on shifts of in the directionality of the wave climate that can be related back to climate indices such as the NAO or ENSO, for example.
Okay,
it's a similar thing with ENSO at Narrabeen.
Okay, thank you very much.
Okay, maybe we can touch on two more questions. So Nicholas Puccino is talking about trying to measure this, I guess. Would the changes observed in the lower shore face be trackable or correlatable to subaerial beach face landform change? Considering the morphodynamic model, I would assume so.
You kind of got to go into many decades, centuries, geological time scales to really see evidence of this stuff. And it's the early, and some of Mike's work as well that I cited there from the Foster-Tuncurry barrier, where if you've got a prograding barrier, you can then, you can get a known rate of shoreline progradation from that. Presumably you can get a rate of relative sea level rise from somewhere. You can then look at what the potential longshore inputs are to the system, either headland bypassing or just longshore transport gradients. And then again, through a process of elimination, you can create a model that determines a given rate of onshore transport is consistent with the rate of barrier progradation that you're seeing. So that's one strong line of evidence fairly strong line of evidence that is still indirect in some way. And then I think there are sufficiently long records in the Netherlands where they've determined there are observable amounts of change, so it's observed directly. And I think, maybe check with Mike, that might be the case for the northwest of the US as well, where you've got a rapidly prograding system, so sort of in Washington State and Oregon, that this type of process can be directly measured. But in general, the rates of change on the lower shore face are less than detectability limits, even for current multi-beam methods for bathymetry. So it's very hard to detect unless you've got a very long shoreline record or one of these other indirect methods, such as a prograding barrier and a fairly solid understanding of the other components of the sediment budget. Oh, I'd add to that as well that Florida example, where it seems like there's a very solid understanding of all the other aspects of the sediment budget, which leaves the only remaining candidate to be transport up from the lower shore face.
The other old-fashioned technique that Brian Greenwood perfected in the Great Lakes is by having stakes bashed into the lower shore face with washers, and basically after big storms you go and remeasure them up, because at least you get the accuracy that you won't have with any sort of bathymetric profile. So
that'd be as good as what we do now.
Hey, well,
that is super useful.
That why don't we do that? Because
it's like when we put ADCPs out and they get buried. It's the best data.
Well, yeah, but if you can imagine the long term, like a couple of cross-shore arrays of big metal stakes that you revisit once a year or something. That would give you the accuracy. The problem only is spatial variability. That is 20 or 50 stakes enough. But the practicality of that sort of work in the UK is that you need 4 divers for health and safety reasons and a boat. That's actually very expensive.
Yeah.
Well, I really think as a community we should be thinking about trying to collect these type of measurements on representative beaches from across the world to really, if we truly are able to understand beach response as sea levels are rising, then having these kind of methods which are accurately being able to answer these questions as a community is where we need to be. My thoughts.
Could I just, sorry, way over time, but do you think for Narrabeen, it is going to look like the variation in the total system budget is much larger than the potential trend lines? Is that what you're seeing already? I think you might have already said, but
well look,
like when you smooth the budget out.
Look, we don't have enough measurements. And now being over 40 years, if you draw a trend, it works out to be nothing. Yeah. So either eventually we'll have to start to see a trend in sea level rise effects, but we haven't seen them yet. So is there something that's offsetting it? And the best measurements we have are the 2016 storm. And then during that extreme storm event, we saw an increase in the order of something like 100 cubic meters per meter, which is quite a lot.
Did that come from the little embayment to the north? Little Narrabeen?
Look,